Welcome pre-cal students to class today on this Tuesday the 25th. Hope you guys are doing well. Hope you're ready to learn some math today. Let's go over some quick announcements here. There will be a quiz on Saturday, so make sure you're looking for that. And unlike the last quiz, I will try to get that out to you early. Your test is due by tomorrow, Wednesday, so please take care of that. Your test is due by tomorrow, Wednesday, and then stay on top of your integrity. Oh, by the way, back to your test. If at all possible, watch that 20-minute video and have your review sheet done so you get 5 bonus points, okay? That would be really helpful for you. And then number 3, stay on top of your integrity sheets. I expect you to be men of integrity, be honest, and do those. Okay, guys? All right. Here we go. Let's get started with taking some notes today. Welcome to Chapter 3, men. We are now heading into Chapter 3, so we're making good time. We did really well on Chapter 2. I would like to come back to Chapter 2 later if we have time and look at some word problems. I really want to do that, and if time permits, we will, and if it doesn't, we won't, so that's fine. We're going to be studying polynomials and rational expressions in this chapter. Those are the two main things that we're going to be focusing on. But today we're going to take polynomials and we are going to classify them. And then after we've classified them, we're going to look at different parts of the polynomials. Okay, so we're going to classify them, learn how to put them in a certain order, look at different parts, and then we're going to look at end behavior of polynomial functions. Now that deals with graphs, okay? And then we're going to test numbers to see if they are zeros. This part here is mega easy. Okay, so that's what we're going to do today. Let's continue on. Write down your heading if you would please. Classifying polynomials. I'm going to get a drink here while you're copying this down. Classifying polynomials, lesson 3.1, and the date today is the 25th. All right, let's continue on. Here we go. Let's start off with a definition of a polynomial expression or function. And of course, don't be confused. An expression would just be an algebra expression with no equal sign. It doesn't have an equal sign, okay? And a function would be, an expression that does have an equal sign, okay? So that's the difference, okay? No big deal there. Okay, polynomial expressions or functions are expressions or functions, now listen, in which all coefficients are real numbers, no imaginary numbers, and all of the exponents of the variables are whole numbers, okay? Now think what a whole number is. A whole number starts at 0 and goes to the right, 1, 2, 3, 4, etc. So when I say all of your exponents are whole numbers, that also eliminates negative numbers, because the true definition of a whole number is starting at 0 and going to the right on a number line, not including fractions, of course, and decimals, okay? All right. Now, you can turn to page 254. You don't need to, but you can if you want to. Here are some examples of polynomial functions, and you can view these on page 254. Now, I don't want you to pay, if you do turn in your book to page 254, I don't want you paying any attention to this stuff here that I've blotted out. Please just ignore that, okay? And we're going to look at that later. That's just confusing, okay? Here's a function. Here's a polynomial function. Here's one. Here's one. These are all polynomial functions. Notice all of the coefficients are real numbers. 4 is a coefficient. Here's a 1 right here. 1's a coefficient. 3's a coefficient. 1.1 is a coefficient. 0.3, 2.8, 2. All of the coefficients are real numbers. Notice all of the exponents of the variables. There's a 1 right here. All of the exponents are whole numbers. None of them are fractions or decimals, and none of them are negative, okay? And I'm not going to test you on this on a test or a quiz. I just wanted to point out to you what a polynomial function is, okay? Or an expression is, and I want to make sure you understood that, all right? Okay, let's continue on. One thing I want to cover today is being able to take a function and write it and be able to write it in standard form. So I want you to copy this function in your notes, and I want us to take this polynomial function and write it in standard form. Are you ready? Let's go ahead and do that right here. Take some really good notes, please. Now, first of all, write this in your notes so you have the problem, and then go ahead and write it in standard form. Now, from now on the rest of the year, when I ask you to write a polynomial function in standard form, that means you start with the highest exponent. In this case, it would be a 3, and that term comes first. You can cross it off. Now, if that would have been a negative right there, be sure and put a negative right here, okay? Be sure and keep the correct sign. Well, the next highest exponent I see is this term right here, and it's positive, so I'm going to put positive 2x squared. Well, the next highest exponent I see is a 1, negative 11x to the 1 power. So next would be negative 11x. You don't have to put that 1 right there if you don't want to. And then lastly comes your constant term, which is negative 12. There we go. Okay? So you just took a function and you wrote it in standard form. Now, Matthew, Caleb, I would like to not give you another example of that, okay? I would like to just do one of these in class, and you'll have some in your homework. It's so easy. You put the highest exponent first, and then descend, okay? I almost said condescend. That's weird. Descend, going down lower and lower, okay? And that's all you're doing when you're writing a polynomial function in standard form. Now, what if I asked you what the lead coefficient was? Please pay attention. A lot of students would look at this function and say, oh, I know what the lead coefficient is. Lead means first, so it must mean the first coefficient. So my lead coefficient would be 2, and that's incorrect. You never know what the lead coefficient is until you first write it in standard form. Okay, so now that I've written it in standard form, here's your lead coefficient right here. It's a 1. It's the coefficient of your first term. So the lead coefficient for this polynomial function would be 1. Let me say that again. You never want to find the lead coefficient until you have first written the polynomial function in standard form. Okay? Or if you like to look up here and find the highest power and look at that coefficient right there, that's fine also. But the point is you can never assume that this first number is always going to be your lead coefficient. It might be or it might not be. Okay? All right, let's continue on. And by the way, I'm just giving you one example of this. It's very easy, and you can do some in your homework. Okay, I'm going to give you one example of what a degree is. Okay, now when I ask you what the degree of a polynomial function is, it's going to be the highest exponent. So as you look over here and you notice this is your highest exponent, then we know we're going to call this a third degree. So what degree is this polynomial function? Third degree. Now again, you don't have to write this in standard form to know that, but make sure you understand it's not the first number right here, this 2. It's the highest exponent. In this case, it's a 3, okay? So the degree of a polynomial function is always the highest exponent. Now let's classify this polynomial function. Don't forget, this was a what degree? Third degree. Because you can't classify the polynomial function until you know what degree it is. And then once you know what degree it is, then you're able to classify the polynomial function, okay? Let me write some stuff off to the side here you need to see, okay? If your degree is 0, we call that a constant function. You will want to write all of this in your notes. I should have had it typed. I apologize. If your degree is 1, we call that a linear function. If your degree is 2, you should know this one, guys. If your degree is 2, we call that a quadratic function. If your degree is 3, we call that a cubic function. So let's come over here. We're going to classify this polynomial function. It's a third degree, so the classification of this polynomial function would be a cubic function. This is a cubic function. If it's a fourth degree, we call that a quartic function, and that's as high as they go. From there on, you would just say it's a fifth degree, sixth degree, whatever, okay? We call this a quartic function, all right? So there we go. You do need to know these. Now you might say, Mr. Earhart, how could you have a degree of 0? Well, I'm glad you asked. If I said f of x equals 3, and that was my function, I could also put x to the 0 right there. I really could. And of course, right away you're saying, no, you can't, because x to the 0 is 0, and 0 times 3 is 0. No, no, no. Anything to the 0 power is 1. Anything to the 0 power is 1. So if I put x to the 0 here, I'm really putting 3 times 1, okay, which is still 3. So if you're ever given a polynomial function like this that has no variable, then assume you have an x to the 0 here, and we call that a constant function. You say, well, how can you have a linear? Well, if you have no exponent, if your highest exponent is a 1, then that's going to be a linear function. Okay, so make sure you're familiar with these names, and do be able to classify these in your homework tonight. Pretty simple, isn't it, guys? I mean, writing it in standard form, telling me the lead coefficient, and then telling me the classification. All right, pretty simple. All right, moving on to another topic now. Let's go ahead and look at end behavior of polynomial graphs. End behavior of polynomial graphs. Okay, lesson 3.1, of course the data is still the same. End behavior of polynomial graphs. Let me get a drink here real quick. And here we go. It is possible and quite easy to know what direction the end of the graphs will be traveling on the right and left sides of a polynomial graph. Isn't that cool? Just by observing the lead coefficient and the degree. So now you're seeing why it's so important to know what a lead coefficient is and what a degree is. It's possible to know what direction the graph will be traveling without even seeing the graph by just looking at the lead coefficient and the degree. Let me show you. Okay, this is really cool. Now you're going to want to take a lot of notes on this, so be ready. All right. Notice right here we have a, take some notes on this. Notice right here that we have a polynomial function that has, are you ready? Watch this. An even, I would write down the polynomial function in a quick little grid, okay? Notice you have an even degree and a positive lead coefficient, a positive 1. Let me say that again. Notice you have an even degree, 2, 4, 6, 8, 10, 12, whatever, and your lead coefficient is positive. When that happens, I mean, the graph might do all kinds of things in between. Okay, it might go up and down, all that kind of stuff. Okay, it might do all kinds of stuff, but you know this one thing. In the end, the graph will go up, and it will never come down again to the left, and then it might do a bunch of stuff in between. We don't know what it's going to do, and then it's going to go up to the right. So you know that. Guaranteed. Sorry, excuse me. Guaranteed, every time your degree is even and your lead coefficient is positive, in the end, it might do all kinds of turns and twists, but in the end, when it's all done doing all of its twists and turns, it will go up to the left and it won't come down again, and it will go up to the right and it won't come down again. Let's take a look at this one over here. Notice your degree is even, so please take some notes on that. Notice your degree is 2, that's an even number. And notice your lead coefficient is negative. It's a negative 1. Well, anytime your lead coefficient is negative and your degree is even, it's going to go down to the left, and it might do all kinds of turns in here. I'm not sure what it's going to do, and then it will go down to the right. Okay? Isn't that cool? That's so helpful. It might take all kinds of turns here in the middle, but in the end it will go down to the left and not come up again, and it will go down to the right and not come up again. All right, let's take a look at 2 more examples. Now, go ahead and copy these in your notes, please. Notice for this example here, we have a degree that is odd, and I really think I should have slid these down a little bit to give me a little more room to write. Let me do that real quick here. Okay, here we go. Notice here, your degree is odd, it's a 3. If you had like a 1, 3, 5, 7, 9, and notice your lead coefficient is positive. Okay, now if that happens, it's going to do it might do all kinds of turns in the middle, but in the end it'll go down to the left and it will go up to the right. Okay, over here notice your degree is odd, and your lead coefficient is negative. So whenever your degree is odd and your lead coefficient is negative, it might do all kinds of turns and twists, but in the end, it will go up to the left over here, and it will go down to the right over here. These are so helpful, men. Guys, listen to me. I'm telling you, when we start graphing these, one of the things you're going to want to know is how many turns does it take, and we'll talk about that later, not today. And then you're going to want to know what the end characteristics are, the end behavior. That's very helpful, okay? Very helpful. Now I'd like you, if you would, guys, to turn to page 258, and let's take a look at example 1. Now you might want to pause the video while you go get your books. You're going to need them because you're going to look at 4 different graphs. I'm going to go ahead and keep teaching, so you might want to pause the video. Turn to page 258 and take a look at example 1. It says, using the leading term, or what we just did, test, match each of the following functions with one of the graphs A through D which follow. Now, I would like to start off with this one here. Basically what they're asking you is, look at the end behavior. Now for this example here, notice I have an even degree and a positive lead coefficient. Even degree, positive lead coefficient. Let's go back 2 pages. Look at this right here. Even degree, positive lead coefficient, up to the left, up to the right. So let's look at a graph that goes up to the left and up to the right in the end. Would that not be letter D? Sure it would be. Look at letter D. D goes up to the left and up to the right, and it doesn't come down again. Okay? We don't care about what it does in the middle. We're talking about in the end. It goes up to the left and up to the right. Look at this example here. Now, notice your degree is odd. Your lead coefficient is negative. So we're looking for one that has an odd degree, negative lead coefficient right here. Odd degree, negative lead coefficient. The graph will go up to the left and it will go down to the right. We'll look at letter B. B is in boy. Look at letter B. B goes up to the left and down to the right. So just with the knowledge you had, you were able to match up graphs, okay? All right, let's take a look at the next function here. Notice I have an odd degree and a positive lead coefficient. Odd degree, positive. Here it is right here. Odd degree, positive. Down to the left, up to the right. Down to the left, up to the right. Well, that's going to be letter A. If you'll look at letter A, you'll see it's going down to the left and up to the right. Now let's take a, excuse me. Now let's take a look at this example. We have an even degree and a negative lead coefficient. Even degree, negative lead coefficient. Here it is. Even degree, negative lead coefficient. Down to the left, down to the right. So that's obviously going to be letter C. Down to the left, down to the right. Okay? Man, the video is almost over, guys. This has been really simple today. Really, really simple. Okay? So that's it. I want you to learn this in behavior, know it very well, and memorize it. Okay? You're going to need to know it for tests and quizzes. And then last, this is so easy. Let's test some numbers for zeros. Okay? Let's test some numbers for zeros. Lesson 3.1. Now, listen to me very carefully, please, men. Don't take notes on this problem, okay? How many times has a teacher said that? Not very often, that's for sure. But I'm telling you, don't take notes on this problem. Just watch. What if I told you to find the zeros for this function? Well, you should know by now that when I tell you to find the zeros, I'm really asking you to find the x-intercepts. And whenever I ask you to find the x-intercepts, you put 0 in for y. So if I asked you to find the zeros for this function, you would put a 0 in for y, and you would solve. You'd bring the 18 over and make it negative. Divide both sides by 6, and you would get negative 3. So you just found the x-intercept, or the zeros of the function. It's negative 3, correct? Now, can we turn this problem around? Remember, I told you not to take notes, just listen. Can we turn this problem around, please? Did I put a 3 here? I'm sorry, it doesn't make any sense. Why did I do that? Negative 3 equals x. There we go. Sorry about that. Can we turn this problem around? What if I would have said this? What if I said, hey, guys, is negative 3 a 0? Or in other words, is negative 3 an x-intercept? All that you have to do is substitute negative 3 in for x and see if you get out the number 0. And if you get out 0, then you know that negative 3 is one of your x-intercepts. Or in other words, you know negative 3 is one of your zeros. And now you're seeing why we call negative 3 as 0. It's because when you put negative 3 in, f of negative 3, what do we get out? Well, 6 times negative 3 is negative 18, and negative 18 plus 18 is 0. So when I put, what this expression means is when I put negative 3 in, I got out a 0. So I've taught you guys in the past, you've learned it well, how to find zeros. You know to put a 0 in for y and solve the equation. But let's turn it around. What if I give you a number and I say, hey, is that a 0? Is that an x-intercept for the function? It's really easy. Just put the number in, simplify, and see if you get a 0. And if you do, then you can say, yes, this number right here is one of my zeros. Okay, so with that in mind, and we're finished for the whole day. Let's just do this. I want you to tell me if 2 and negative 5 are zeros of p of x. And here's p of x over here. Guys, this is so easy. Let's test 2 first of all, okay? So we're going to put in p of 2. P of 2 equals, are you ready? 2 to the third power plus 2 squared minus 17 times 2 plus 15. Everywhere there's an x, I put a 2 in, and we're going to see if we get out a 0. 2 times 2 times 2 is 8. 2 times 2 is 4. 17 times 2, negative 17 is a negative 34, plus 15. Alright, well, if you add up all of your positives, you get 27. Bring down your negative. 27 minus 34 would be negative 7. So P of 2 equals negative 7. Did I get out a 0? No, I did not. So is 2 one of your zeros? No. So the answer to 2 is no. Isn't that easy? One more example like that and we're finished. It's not difficult. Okay? Is negative 5 a 0? Well, let's find out. We're going to put in P of negative 5 equals, alright, and I don't have my calculator with me. I wish I did. I should have. We'll try to do this in our heads and hopefully we'll get it right. Negative 5 squared minus 17 times negative 5, positive 15. Alright, here we go. Negative 5 to the third power is going to be negative 125. Negative, negative, negative is a negative, and 5 times 5 times 5 is 125. And then here we have a negative 5 squared. So a negative 5 times a negative 5 is 25, and there's a positive sign out front, and a positive positive is a positive 25. Now we have a negative times a negative, that's going to be a positive, and that's going to be 85, 17 times 5. And then bring down your positive 15. Okay, if you combine all your negative numbers, you get negative 125. If you combine all your positive numbers, you get 5, 5, 10, 15, 5, carrier 1, 3, 11, 12. You get a positive 125. And of course, when you combine those two numbers, you get P of negative 5 equals 0. So when I put negative 5 in, did I get out a 0? Yes. So is negative 5 one of your zeros? Yes. So in other words, if you were to graph this, remember they can have more than one x-intercept. I mean, the graph might go like this. It might have 1, 2, 3, 4, 5 x-intercepts, okay? I'm not referring to this. I mean just any polynomial function. So there might be more than one, but is negative 5 a 0? Yes, it is. Yes, it is. I hope you've listened well. I hope you're doing well on your test. Call or email if you have any questions at all, guys. And here is your homework, page 265, 1 through 25 odd, only about 13 problems, so a pretty small assignment. Please get to work on that and call or email if you have any questions at all. Okay? Have a good day.